Hello, everyone. Thank you all for coming to my talk today. Today, I'd like to tell you about my work on hardware-accelerated Bayesian machine learning for applications in quantum sensing. Okay, so what is Bayesian machine learning? Well, there's a specific kind of machine learning that we do using Bayesian statistics. It's called optimal Bayesian experiment design. So what is optimal Bayesian experiment design? We call it OBED. OBED is an experimental technique that we use to reduce the number of data points needed to make a measurement. This differs from the more familiar scan and fit measurement technique that involves taking a lot of data in sequential fashion and then fitting at the end of the scan to extract the parameter of interest. The scan and fit technique requires just let me turn my pointer on here, requires a lot of data for averaging if your signal to noise of your measurement is low. And this is especially problematic if you need a large scan range because the thing you're looking for moves around a lot, or you aren't too sure where it is in the first place. For example, trying to find an optically detected magnetic resonance frequency for a single nitrogen vacancy center using the standard scan and fit technique can require over 1 million data points collected over 140 scans just to get an accurate fit for the resonance frequency, shown as this little dip here, fit for the resonance frequency of interest. In these cases, much of the time spent in your ODMR spectrum is wasted collecting data points that don't meaningfully contribute to your fit. But what if there was a way you could only measure the good stuff? What if you could just measure the area around a region of interest without actually having to waste time measuring all these other data points that don't contribute anything useful? OBED is an experimental technique that does precisely that. By using previously collected data points to decide the experimental settings used to collect the next data point. And this often results in orders of magnitude less data points required to make an accurate measurement, but comes at the cost of increased computational time spent between measurements. So how does OBED only measure the good stuff? OBED is a computational technique that uses experimental data to suggest which experimental settings are likeliest to result in a good measurement. To do this, it must first determine how well the measured data agrees with the your physical model for the system. This physical model could be any function that describes the behavior of the system as a function of model parameters. For example, amplitude and phase for sinusoidally varying data, or peak amplitude, full of half max, resonance frequency, and offset for optically detected magnetic resonance measurements. This is done in a two-step Bayesian inference subroutine, where the probability that the model function describes the measured data point is calculated using a Gaussian function of the experimental noise, that's sigma, and the collected data point value, which is y sub n, and the model function here, which is f of the model parameters theta and the experimental settings used to make the point d sub n. This probability calculation is performed for the full set of model functions built from all possible combinations of the model parameters theta and model parameters theta, forming what's called a likelihood set, which is then updated using Bayes' rule with the prior likelihood set from the previous measurements, forming the posterior probability distribution known as the posterior. The experiment design subroutine uses the posterior probability distribution to find which experimental settings result in the largest increase in relative entropy from the previous measurement. The experimental setting with the largest relative entropy is likeliest to result in a good measurement. How is OBED implemented in a real experiment? So we introduced the OBED software calculation between data collection and the setting selection steps for our nitrogen vacancy magnetometer apparatus. This system uses a nitrogen vacancy diamond, an NV diamond excited by a laser whose photoluminescence amplitude decreases when an applied microwave field is at its magnetic resonance frequency. This optically detected magnetic resonance frequency changes as a function of the magnetic field environment around the diamond, allowing magnetic field information to be read out optically via the diamond NV diamond photoluminescence. The ODMR acquisition time is set so that the signal to noise of the measurement, signal to noise ratio of the measurement is near 1, and the performance of the OBED technique is compared to the scan and fick technique. The scan and fick technique collects 8,000 photoluminescence amplitude data points as a function of frequency of the applied microwave field, generating an ODMR spectrum. This ODMR spectrum is then used. This ODMR spectrum is averaged many times, and the ODMR resonance frequency extracted from the fit to the ODMR spectrum is plotted as a function of the number of data points, where each dot here represents 8,000 data points, which is 1 scan for the collect and fit method. The OBED technique starts with a random frequency setting for the first measurements, and every subsequent measurement is performed with a microwave frequency setting determined by OBED. The ODMR resonance frequency determined by OBED is also plotted as a function of the number of data points. And the OBED method is found to require 40-fold less data to achieve the accuracy in the ODMR resonance frequency to achieve the same accuracy in the ODMR resonance frequency as the scan and fit method, and can operate at a measurement bandwidth of 100 Hertz, depending on the computational hardware. So far, the experimental performance of our software OBED tool has been pretty impressive, but it's only really applicable in situations where the rate at which you take data is much slower than the time it takes to perform an OBED computation. In our case, that limits us to about 100 measurements per second. Some experiments can collect data at a much faster rate. For OBED to be useful in those situations, you need to have either a faster computer or a faster OBED calculation. Since computational resources are ultimately finite, we investigated what computational bottlenecks were holding the OBED software back. It turns out that most of the time in an OBED calculation is spent determining the utility function. It's this guy right here, which is in the experiment design step. To address this bottleneck, we need to find a utility function that is easier to calculate. In general, a utility function is just an expression for the relative entropy between the previous measurement and the next, the relative increase in entropy. This is determined by evaluating this sum involving a double integral over all possible measurement values and all possible experimental parameters. This is obviously computationally unfeasible for high-speed measurements, but it turns out that you can make a few simplifying assumptions to reduce this to a much easier function to evaluate. If, for example, you assume that the experimental noise is Gaussian, you can reduce this double integral to a statistical range of a small sample of model function values. Since this statistical range is just a difference between the maximum and minimum values of the set, this is much simpler to calculate than the double integral. This min-max utility function results in about a 10-fold reduction in time spent in the experiment design subroutine calculating the utility function, and provides an overall 2.5-fold improvement in processing time for the OBED calculations. This improvement in measurement bandwidth of our software OBED implementation, it improves the measurement bandwidth of our software OBED implementation to 250 Hertz. Furthermore, it turns out that there is basically no penalty to your rate of convergence to an accurate measurement result when compared to other utility functions, including the full relative entropy utility function. You can see that in this plot here, which is standard deviation of your parameter of interest as a function of number of data points, and for all the various different kinds of utility functions, and they all perform at almost exactly the same rate. All converge at almost exactly the same rate as the min-max, and the min-max only requires, like 1/10 the time to calculate. So 250 Hertz bandwidth is sufficient for slow measurements that need long acquisition times to achieve a reasonable signal to noise ratio. But what if you have a good signal to noise ratio at shorter acquisition times? For example, magnetic field sensing with ensembles of NV centers is one example of this. where the emission rate of the ensemble is high enough that photon counting is no longer necessary. And a photodiode is all that you need to do your data collection. A typical photodiode has a bandwidth on the order of about 1 megahertz, which is much too fast for even the fastest computer running our latest min-max OBED software. In order to extend the usability of OBED to measurements of this kind, hardware accelerating the OBED computation is an attractive solution. Hardware accelerated OBED is no simple task, however, as it has unique design requirements due to its inherent computational complexity. Generally, when the number of unique operations is high, a general purpose CPU is the tool of choice for arbitrary mathematical calculations. However, despite being computationally complex, OBED is highly parallelizable, and the number of parallel computations that a CPU can perform is limited. Highly parallel calculations are often amenable to acceleration using a GPU, using GPU's thousands of computational pipelines. While OBED is highly parallelizable, each individual calculation is generally too complex for the GPU to manage, given that they excel at doing many simple things like simple calculations like multiplication and addition in parallel. This leaves the FPGA as our tool of choice for accelerating OBED. In an FPGA, it is possible to create many custom computational pipelines with specialized arithmetic in parallel, which is exactly what OBED requires. So we developed an OBED hardware architecture suitable for use in an FPGA based around custom designed Bayesian compute cores that implement the higher speed algorithms developed previously, like the min-max utility function and a quartic evaluation of the Gaussian likelihood. Hundreds of these Bayesian compute cores can be instantiated in parallel to batch process the entire space of model function parameters and candidate experimental settings in just a few clock cycles, resulting in a projected measurement bandwidth of over 1 megahertz, while possessing a similar convergence rate compared to the software OBED method, which we compared running 500 data points. So after 500 data points, we determined that we had maxed out the accuracy using the software method, and that was done with signal to noise ratios between 3 and 4. So it's quite competitive. All right, so just as a quick recap, software OBED is ideal for improving efficiency in slow measurements, while hardware accelerated OBED can extend this improvement to efficiency to measurements that are over 1,000 times faster than what OBED can handle. Both of these techniques fit with our general design philosophy for OBED, meaning that they are completely general and application agnostic, user customizable, and provided as free open source software on our group's GitHub page. So with that, I'd like to thank you all for coming and thank you for listening to my talk. If you have any questions, please feel free to ask them now, or you can contact me at my email address here at NIST. You can also check out our software. We provide it free and open source on our group's GitHub page. And lastly, I'd like to acknowledge my postdoc advisor and Robert McMichael and my colleagues Sergey Dushenko and Jaden Kraft. Thank you so much.